Hello viewers, welcome to this exciting video. In this video we will be looking at the 2020 Science Paper 1 GCE question C3. Question C3 is a question dealing with atomic physics, popularly known as radioactivity, and it reads, a radioactive substance B has a half-life of 4 years and undergoes reactivity by giving out beta radiation. A radioactive substance B has a half-life of 4 years and undergoes radioactivity by giving out beta radiation. A. Which of the containers, aluminum, thin plastic, or lead lined, would you use to safely store substance B? Which of the containers, aluminum, thin plastic, or lead, lead line, would you use to safely store substance B? All right. Now, it's not all about what can stop beta radiation. It's all about safety. Okay. So the key word there is safety. Okay. And we know that this substance is emitting beta radiation. Now, from what we basically understand about radioactivity is that alpha particles are stopped by paper, air, and the skin. Those can stop alpha, but however, there is always a limitation to how much of that given substance will manage to get the job done effectively. Okay? For beta radiation, we know that beta radiation will pass through plastic, they will pass through paper, and eventually they may pass through skin. Therefore, we know that aluminium, a few millimeters of aluminium will stop beta radiation. So a few millimeters, remember they tell us that it should be a few millimeters of aluminium, okay? Meaning there is a threshold in thickness. So there is a certain thickness. If the aluminium is too thick, a certain amount of beta radiation may pass through. Okay, so then we go to lead. Lead stops the most penetrative radiation, which is gamma. Okay, meaning that beta cannot pass through completely through lead. So in terms of safety, we are going to say that lead is the best choice. Okay, because aluminium, depending on the thickness of the aluminium, certain radiations may manage to penetrate through. However, lead, regardless of the thickness, alpha or beta particles will not be able to pass through. So the best choice is a lead lined container. A lead lined container. All right, let's go to C. So lead lined container. Let's go to B. B is saying copy and complete table C3.1. Copy and complete table C3.1. So we are supposed to finish this. Okay. Now, they've given us dates. 1st July 2008. That is the starting day. There was 8 grams of the substance. Okay. Then on the same day in 2012, they want us to find how much would have remained. And on the same day in 2020, they also want us to find. So how do we answer such a question? This question is very easy. So in 2008, so I'll do this. In 2008, okay, in 2008, we had 8 kilograms of the substance. Okay. However, the question is saying this substance has a half-life of 4 years. So after 4 years, so 2008 plus 4 will take us to 2012. So after 2012, this will reduce to half. So what is half of 8? It's 4 kilograms. So 4 kilograms remains. So in 2012, we have 4 kilograms. So we write 4 kilograms. Then after another 4 years, so 2012 plus 4 takes us to 2016. In 2016, half of 4 remains, which is 4 divided by 2, which is 2 kilograms. However, we have no year here corresponding to 2016. So we continue. So again, after another 4 years, so 2016 plus 4 takes us to 2020, the year 2020. So what remains? Half of the 2 kilograms, which is 1 kilograms. So in the year 2020, we are remaining with just 1 kilograms. So the table is complete. The table is complete. All right. So that gets you your 2 marks. 1 mark obviously for each correctly stated answer. All right. Then let's proceed. Let's proceed to C. C is saying a Geiger counter was used to measure the activity in counts per minute from a radioactive sample in the laboratory over a period of years. However, over this period, the background radiation was regularly measured at 4 counts per minute. Okay? A Geiger counter was used to measure the activity in counts per minute from the radioactive sample in the laboratory over a period of years. Over this period, the background radiation was regularly measured at 4 counts per minute. So here, they've given us the background count. What is the background count? It is the count rate due to background radiations. And what about background radiations? Background radiations are radioactive radiations that are always present in the environment. They are there, and their sources are mostly due to rocks, radioactive rocks, okay, and also cosmic rays. Now, take note, for us to build a house, okay, there should be rocks that should be crushed somewhere so that they use them to make either blocks or mortar that is used to make the walls around us. So there is always radioactive radiations from such walls, okay, and they account for what is called background radiation. All right, now let's okay, so there is our table. Okay, there is a time in years, so we have 0, 1, 2, 3, 4, 5, 6. Then we've got the recorded activity in counts per minute. We've got 124 all through 12. Then we've got activity due to the sample. Now, the activity due to the sample is after you've now removed the background count from the recorded count, from the recorded activity. So, copy and complete table C 3.2 on the activity of the sample alone. So we need to just complete this by subtracting 4 from the recorded count. So we start 124 minus 4 is 120. 80 minus 4, it's 76. 52 minus 4 is 48. 34 minus 4 is 30. 23 minus 4 is 19. 16 minus 4 is 12. So that is all that we needed to do there. Okay, that is all that we needed to do there. Okay, then they're saying explain what is meant by background radiation. I already said that background radiation is radiation that is always present in the environment. This is radioactive radiations that are always present in the environment. And we talked about the sources also: cosmic rays, rocks, okay? All right. 3. Plot a graph of the value for activity due to the sample alone against time. Activity due to the sample alone against what? Time. 4 marks. These questions are mostly given 4 marks. All right. So let's proceed to our graph table, to our graph paper. So that is, here is our graph paper with the axis already drawn. I keep reminding, there should always be arrows there, okay? There should always be arrows. Now, first things first, before we continue, we need to write the title. They've said activity due to the sample alone against what? Time. So activity due to the sample against activity activity due to the sample alone, due to the sample due to the sample alone against time. Then we underline that. We are done. Then now we start, we go. The next thing is labeling of the axis. Labeling of the axis. So here, the activity due to the sample alone has the same units as the activity recorded. So it's count per minute. So activity due to the sample alone, and we have the time. Time is in years, so we come to the x-axis. We say time. Time is in what? In years. All right. Then we go to activity due to the sample alone. All right. So we have labeled the y-axis, activity due to the sample alone in counts per minute, and we have time in years for the x-axis. Now it's now time to actually come up with a scale. The scale is relatively easy, especially if you can work with your calculator. The more you try it out, the better you become. Now always take note. I mostly advise people to use about 7 boxes on the y and 8 boxes on the y and 8 boxes on the x-axis. That will give us a graph that is more than 3/4 of the whole entire graph paper, or that is that covers 3/4 of the whole entire graph paper. Now, I've said to myself, okay, sometimes dealing with guessing games is a bit tricky. However, what I'm going to do is that I know it may be hard to understand it, it may sound tedious, but the more you use the method, the better you become, and the more fast or quick you become at coming up with values. So what we are using is, we are using this, and we are also using those. So time is on the x-axis. Now, how many points do we have? We have 1, 2, 3, 4, 5, 6, 7 points. We have 7. However, we are supposed to use about 8 boxes. So what I do is, the procedure is relatively easy. So what I do is the biggest number minus the smallest number. So that is 6 on the x-axis. So this is for x-axis. So this is for the x-axis. I say 6 minus 0. Then the difference here, I'll divide it by the number of boxes I want to use, which is 8. So 6 minus 0, this gives me 6. 6 divided by 8. Okay, what is 6 divided by 8? So 6 divided by 8 is 0.75. So it means that between every 2 centimeters, it will be increasing by 0.75. 0.75. So between each, so I now go to the x-axis, so I'll put my 0 there. So 0 plus 0.75, it will be 0.75. 0.75 plus 0.75 is 1.50. 1.50 plus 0.75, this gives me 2.25. 2.25 plus 0.75 is 3.00. 3.00 plus it's 3.75. 3.75 plus 0.7, that gives me 4.50. 4.50 plus 0.75 gives me 5.20. 5.25. 5.25. 5.25 plus 0 point, that's 6.00, which is 6. All right, so that is how I usually do things. I know it is difficult because when we come to now locate points, it is a bit tedious. However, if you have a calculator near you, it's relatively easy. Okay, then we now go to the y-axis. We'll do the same for the y. So what is the biggest value for y? The biggest value is 120, the smallest is 8. So we are going to have, this is for the y-axis. For the y-axis. So for the y-axis, I'll have 120 minus 8 over 8. So 120 minus 8, I'm going to have something like 112. 112 divided by 8. So what is 112 divided by 8? 112 divided by 8, this is 14. So it will be increasing by 14. So it will be increasing by 14. So 14. What we now start doing is we come to the y-axis. Then we'll start here. It's not 0, it's going to be 8. This is 8. Okay, so this is not 0, 0, it's not the origin. Okay, it's 0.8. This point is 0.8. It's not 0.0. So now once we do this, okay, what we're going to now start doing is increase this by 14. So I have 8 plus 14, I'll have 22. 22 plus 14, I'll have 36. 36. 36 plus 14, I'll have a 15. 50. 50 plus 14, I'll have a 64. 64 plus 14, I have 78. 78 plus 14, I have a 92. 92. 92 plus 14, I have 106. 106 plus 14, I have 120. All right, so there. So we have now all the two axes, they've been labeled, and the scales are correct. All right, now we start plotting. So let's just do this. Since on the x-axis I need it is increasing, it's 1, 2, 3, 4, 5. So I'll start here first, so that I locate all the whole, where the whole numbers are most likely to be, or maybe we just get the coordinates themselves. Okay, coordinates. So let's do this. Really occupy a large portion of our screen. All right, we now start plotting. So the first and the last points are almost just plotted out for you. So the first point is 0. We have 0 and we have 120. So which is right about here. So that is where 0 and 120 are. Okay, 0, 120. The next is 1, 76. 1, 0.76. So we need to locate where 1 is. So I'll say 0.75. Each one of these is 0.75 divided by 10, which is 0.075. So I'll start adding. So I go to my calculator. I say, okay, let me just minimize that. Okay, I go to my calculator. Then I say 0.75 plus 0.075. That is the first line. So the first line gives me 0.825. The second line gives me 0.9. The third line gives me 0.975, which is almost 1. This is the third line. So I go back, okay, to the third line. So from 0.75, I have 1, 2, 3. It's somewhere here. Okay, 1 is somewhere there on the third. So what am I going to do now? I'll follow now. I'm looking for what? It's 1,76. So 1,76, where is 76 most likely to be? Now remember, one of these on the y-axis is a 1.4 because it's 14 divided by 10. It's a 1.4. I'm looking for 76. So 76 lies slightly below 78. So what I'm going to do is I go back again to the calculator. I say 78 minus 1.4. So which is 76.6. If I say minus 1.4 again, I go to 75. So I just drop by 1. So I'll just drop by 1 box. So from here I drop by 1 box. So it's somewhere here. So now I have 75. Okay, 1, 1, 2. So where is 75? Okay, so this line. Okay, then I drop twice, which is there. Let's just verify. Okay, correct. So this is where my next point is. So that is where my next point is. Then I go to the next point. The next point is 2,48. 2,48. 2,48. So 2 should be just slightly below this. So 2.2. So I'll say 2.2. So 2.25 minus 0.075, which that is the first one. 1, 2, 3. So the third line again, the third point. So 1, 2, 3, somewhere here. Okay. Then here I have 48. It's supposed to be 48. So 48 is just below 50. So again, I'll say 50 minus 1.4, which is 48.6. I can't drop any further than this because it will be too small. So again, just 1 below 50. So it's somewhere here. Just I follow this one. So just there, just here, then right across there. The next point is 3,30. 3,30. 30 is just below 36. 30 is just below 36. 30 is just below 36. Okay. 30 is just below 36. So I'll say 36, clear 36 minus 1.4, which is, that is 1, 1, 2, 3, 4. So the fourth dot. So the fourth from here, which is 1, 2, 3, 4, right here. So this is where my cross will be. Okay, then I go to the next, which is 4 and 19. 4 and 19. Where is 19? Okay, where is 4? 4 is just above 0.35. So 0.375. We are adding 0. 3.75 plus 0.075. That is our first point. 1, 2, 3. The third line. So the third line from here, which is 1, 2, 3. So here, this is where, and 22, the 19 is just below 22. So 22 minus 1.4. That is the first box. That is the second box. So we're coming to the second. So 1, 2, second box, and it's here. Okay, it's there. There is our point. The next point is 5, 12. 5, 12. 5 is just below 5.25. So 5.25. 5.25 minus 0.075, which is 5.1, minus, that is the second one. Okay, let's just repeat that one. 5.25 minus 0.075. So the first point is there. 1, 2, 3. The third point. So the third, as we move down, which is 1, 2, 3, somewhere here. Okay, so it's somewhere there. Then here we have, it's a 12. 12 is just above 8. So we'll say 8 plus 1.4. So the first point is 9.4. The second point is 10.8. The third point. So we're looking for the third point. So which is 1, 2, 3 there. So this is a point. Then the last one is 8, 6,8. 6,8 is right there. This is where 6,8 is. Okay, after we've done this, we now need to join the points. So we're going to join the points. Okay, now the line should be smooth. So I will just try to zoom in a bit so that since I can't rub, if I make a mistake, it's not like I'm using a pencil. So I'll start from my first point, which is there. Technology is failing me. All right. Okay, when I reach that point, what I do is I try to zoom out a bit so that I can see the last remaining points. Oops, it's not supposed to show any. Yes, oh no. Let's redo that one. Okay, right, like that. All right, let's now try to zoom out and see how the curve looks like. That is our curve. So this is our curve, and that is how it's going to look like. So we have completed everything about this graph. So what we now need to do is go back to the question. There is another question that is there. Okay, use your graph to determine the half-life of the substance. Your graph to determine the half-life. So what we're going to do is we're going to say 120 is the original count rate that we had. So I'll say 120 divided by 2 gives me 60. So I need to look for 60. 60 is just below 64. So I'm going to say 64 minus 1.4. 64 minus 1.4, which is 62. That's the first point below. The second point, the third point, that is almost. Okay, so the third point. So the third point. Okay, so what we're going to do is, okay, let's redo that. 64 minus 1.4. So 1, 2, 3. So the third point. So we come to 64. We look for 1, 2, 3 here. So we'll follow this. Okay, we'll follow this, showing like that. Then this should drop. So you are using a rule. Okay, so that is so close to this line. Okay, that is so close to that line. So we are looking for this. So we are going to record this particular value, which is 1.50. So we are going to say half-life is equal to 1.5 years. So that is our half-life. Thank you very much, viewers, for watching this video. If you like the video, don't forget to give it a thumbs up. If you're new to the channel, don't forget to subscribe and hit the notification bell. Thank you very much.